All right, so you're up on this. All right, class, we're rolling. So let's go ahead and look and see what's going on for this week. So I'm put 3C that I'll do tomorrow. Also note that you have notes on textbook chapter 3, section 4 due tomorrow. Today we're going to talk about the derivative rules. Tomorrow, specifically the product and quotient rule. Wednesday, I think it's going to be calculus and technology. We're looking at a memorization quiz on Thursday and a real quiz on Friday. So make sure you remind me tomorrow, and I'll have that memorization quiz material ready for you. Emily, you need to zoom out and move that around. Something else that we can do right now is I'm going to return to you your quiz, since now everyone has taken it, okay? And if you're happy with your grade, that's great. If you are not happy with your grade, follow me to the back with your eyes at least, and you can swivel that around there. If you're not happy with your grade, then you can grab one of these, the grade correction forms, okay? The quiz and test correction forms. On that, there is a space for you to write the problem, and so you'll need to write the question. If there's a graph, you'll need to kind of sketch it, okay? If there's formulas, whatever, you'll need to write the formulas down. And then go ahead and solve it. Figure out what the right answer is. You can ask me, you can ask somebody else what the correct answer is. And basically, whatever you did wrong, fix it. Solve that problem right here. And then in one or more complete sentences, explain why you missed the problem. Okay, so normally it's not enough just to do it right. You have to name the thought process or the lack of knowledge that was present in order for you to solve the problem. It'll help you to be more aware of that particular problem, make sure it doesn't happen again in the future. And that's why item 3 says, in one or more complete sentences, explain what you will do in the future to prevent yourself from making the same mistake again. So this could be something like, why did you make a mistake? You can say, maybe I forgot to decrease the exponent when taking the derivative, or something like that. What will we do in the future? I will remember the phrase pop down, power down when taking the derivative of polynomials, or something like that, okay? So some things the students have put here in the past that are not acceptable answers would be like, I'll pay more attention, or I will focus. I'm not looking, those are, or why did you miss it? I wasn't thinking right, okay? That is not a helpful corrective mechanism. What we're trying to do is I'm trying to get you very specific here, because the more specific you can be about the problem, then it significantly decreases the likelihood of you making that same mistake again. If like I said in that previous example, if you were to say, I did not decrease the exponent by 1 when I took the derivative of a polynomial, okay? Then you're like, you can think of it, just thinking that out loud and saying that and writing that down is going to help you be more focused the next time you take the derivative of a polynomial. You know what I'm saying? But if you just say, I should have been paying more attention, that's not going to help anybody. Okay, so anyway, what you keep, you'll turn in, let's say you miss questions, 5, 9, and 10, okay? So you do 5 here, 9 here, you'll get another sheet of paper, 10, you'll staple it. I do not need your quiz back. I have an electronic copy. I've got lots of copies. I can print out as many as I want. I don't need a copy of your quiz. I don't need a copy of your answer sheet. All I need is this, okay? And this is a way for you to get points back on your quiz, no matter how many or how few you missed, okay? You missed 1, you got 96, you want to try to get 97, then you can do that, all right? You missed 10 and got a 60, you want to try to go for 70, we can do that, all right? And I'm not telling you 1 point per question, but anyway, if you are the last one to grab one of these sheets, then let me know and I will send you to go make copies. All right, so when you are finished with that, you'll staple it and put just those correction forms over here in the absent box. Like I said, Now this is the way that I curve the class, okay? Is if you do poorly on the quiz, then I give you points back on that. Now, I don't give you points back such that if everyone does the corrections, then everybody shifts up. You still can maintain your relative locations, okay? So whoever got the highest grade still has the highest grade. Whoever has the lowest grade still has the lowest grade, but your lowest grade isn't like way down here. Your lowest grade is kind of up here. Does that make sense? Now you do the corrections and somebody else doesn't do the corrections and you pass them and bump over them, and then, well, shame on them, right? You know, they should have done their corrections.
So then it's only one problem per correction sheet?
Is there only 1 percentage point? No, it depends.
Like one problem on one of those?
No, it's two.
Yeah,
It's
yes.
two.
One on the
per
front,
page.
one on the back. Yeah. It's sort of a way of helping you, you know, I mean, in some cases, there's a motivation of like, man, I want to do good on this test, or I want to do good on this quiz so that my grade is high, or I want to do good on this so that, you know, I have a good average, or my parents are proud of me, or I feel like I've learned something. Or it might be that you're like, I want to do good on this, so I don't have to spend 2 hours writing these questions down all over again. So I'm okay with that too.
When are corrections due?
So when are corrections due? Normally a week after I give the quiz back to you. Okay? I'll put that up there on the board. So here are the questions. Cody's not here. So Ivan, unfortunately yours is not graded. You have to come by at lunch.
Okay.
I've got it. Yeah, right over there. Some room for improvement on that one. So Ivan, like I said, I will give you that.
Sounds good.
What we're probably looking at, since Wednesday and Thursday, I'll probably give you all a little bit of class time to do that, as well as answer some questions. This is going to be kind of a light week, depending on how long that technology thing works, and Thursday and stuff like that. So anyway, we also need to grade the memorization quiz before your next memorization quiz, so we'll take care of that too. But I do want to get into a little bit of calculus this morning, so let's go ahead and do that together right now. So, some of this is going to be sort of like a list activity here. I'd like for us, well, I guess maybe we can go over some stuff we talked about. Talk about the situation. So time we can start thinking. It's Monday. All right. So derivatives. Just you want to make sure that you have this information on your paper somewhere. All the way back to the power rule. So derivative of x to the n is n times x to the n minus 1. Sum and difference property of derivatives. If you have a function which is made up of other functions, adding or subtracting, then the derivative is the sum or difference of their derivatives. So if you have g of x plus h of x, then the derivative is g prime plus h prime. The constant multiple rule, that is that if you have a function is equal to a constant times a polynomial here, so x to the n, so c times x to the n, the derivative is c times n, so pop down the exponent there and then power down n minus 1. And then we saw all of this taking into effect with those graphs, right? We saw that a quadratic graph can take a derivative, turns into linear, so on and so forth. So, what are some things that we could do here? adding on like derivative rules, I guess is what this title, this lesson's all about. We already talked about the power rule, where x to the n goes to, we take the derivative n x to the n minus 1. Sum and difference rule. One thing, is we've got the constant multiple rule. What other ones do we have here? Which is kind of helpful to, we need to talk about a constant, like the derivative of a constant. Actually, it's not constant rule, it's just the derivative of a constant. Draw a couple grids here. So what is a constant function? Well, a constant function would be something like f of x equals 5. Class, what does that function look like? F of x equals 5.
A line.
It is a line. Horizontal. So slope. So what's the slope of a horizontal line?
0.
0, yeah. It's 0 right here. 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 So based on the activity from the homework that we did, if we were to plot those derivatives, okay, those slope values at each one of these places, then we would have a y value of 0, slope of 0. You know, we're looking at a y prime that looks like that. So f prime of x is 0. Bearing in mind, I'm going to ask this probably every day for like the next 3 weeks as well. What is the derivative, class? What does that mean?
It's the slope of the tangent.
It's the slope of the tangent line. So when we have a derivative function, this is a formula telling us the slope of the tangent line at any point x. So at this point x, the slope, this tells us we got a y value of 0, which means that this function right up here has a slope of 0. Okay. Now that is in contrast to this formula right here, f of x equals 5x plus 1. What does that function look like, class?
It looks like
Nope.
a line with a slope of 5 over 1.
Yes, and a y-intercept of 1.
In a way.
Yep.
De 9 casi 10.
Excuse me? Oh, I thought you were adding something to the conversation. So yeah, so this right here, this is a linear function. Technically, you could say that this is a linear function with a constant, with no slope, but technically we would call this this is a constant function. This is a linear function, okay? And just to be clear, what's the derivative of this linear function? Emily?
5.
5. Prime of x is 5. We could do that a couple different ways. We can analyze that the way that we did on Friday with local linearization techniques, zooming in, so to speak, and trying to find out what the approximation of tangent line would be there. In each one of these cases, it would be 5. Slope is 5, slope is 5, slope is 5, slope is 5, slope is 5. As a result, when we're plotting that slope as y values here, we could say 5, 5, 5, 5, 5. We also could do that utilizing our power rule, where the power rule says take that exponent right there, which is 1, pop it down, multiply it, so 5 times 1 is 5.
Oh, yeah, 5.
I'll put 5 times 1 just to make it real clear. And then power down, so x to the 0, right? And then this one doesn't have anything, so it's just going to be 0. So this is going to be just 5. That reminds me, what type of a function is this right here, this plus 1? Jeremy? It's a constant, right? And what's the derivative of a constant function?
Oh, it's 0.
0. Yeah.
So that way you don't add it to the.
That's why I could put plus 0 right there. So let's see if we can think about this logically. So if we have f of x equals b, if f of x equals 5 or 7 or 9 or 10 or negative 20 or whatever, the derivative is, anybody? 0. So if you don't have any x terms, you're just looking at a number. You're looking at a constant, and the derivative is 0. So if I told you that g of x was equal to negative 7, that's this graph right here. Ivan, what is g prime of x?
It's going to be 0.
It's going to be 0. You could tell that from the graph, the slope is over here. You can also tell that from the number right there on the function that it's constant, right?
Yes.
I don't know. Maybe I should have started with this, but I feel like it's kind of a weird case. You know what I mean? But all you all really need to know is, yep, the derivative of a constant is 0, and then obviously see the base in there. Chloe, does that make sense? It also is kind of nice here. This one was helpful. I'll write it out a little bit larger here. So f of x equals 5x plus 1. I kind of was doing it sort of on the slide, but in reality I was applying the sum and difference rule here, right? Because what I was asking you was, what's the derivative of 5x? Okay, sort of like this is like a g of x, and y'all said, okay, well that's 5, and then I said plus, what's the derivative of 1? And you said, well, it's 0. Okay, so what I'm getting at is, when you have a function, like here, f of x, which it can be thought of as one function, g of x, plus another function, h of x, then the derivative is the derivative of that first one, so g prime of x, plus the derivative of the second one, h prime of x. And normally Calculus 1 students, you're kind of like, yeah, it's pretty obvious, but as mathematicians, we're very careful to make sure that we don't just jump from saying you can do this and saying you can do this to saying that you can do the derivative of both of them combined. But it's really not very difficult to prove that. Okay. Let's go ahead and apply this really quickly. Or maybe we should, I don't know, we saw that cubics turned into quadratics, quadratics turned into linear. Let's say there's a question that says, find the slope of the tangent line to the function f of x equals 5x cubed plus 10x squared minus 3x plus 7 at x equals 4. Find the slope of the tangent line to the function fx equals 5x cubed plus 10x squared minus 3x plus 7 at x equals 4. So if we wanted to, we could draw that, function to be some sort of cubic and be rather large. But we actually don't even need a calculator for this. We don't want to sketch or anything like that. We're just going to apply this right away. Let's go ahead and let's play the game. What's the derivative here, class? We're going to break it down using the sum and difference property. We're going to take the derivative of that term, then we're going to take the derivative of that term, then we're going to take the derivative of this term, then we're going to take the derivative of that term. Okay? So, Jeremy, what's the derivative of this first term? 5x cubed.
15x squared.
15x squared. Rosa, you were gone, but you would give it a shot. Derivative of 10x squared. Not quite. We don't take the 2 squared here. We just multiply it by. So you said 20x. You are correct. Going down the line here, Nick. What is the derivative of 3x? Not quite. We're not there yet. The derivative of 3x. Anybody else want to give it a shot? 3. I'll put the minus sign. It's linear, Nick. So the derivative of linear is going to be constant. Okay? And you think of it, there's like 1 right there. And then Ivan, the derivative of 7?
0.
Is 0. Okay. Anybody have any questions with that? Are we finished? What do we need there, Hector?
You need to plug in 4.
Yeah, we need to plug in 4. So I'll write that as f prime of 4 equals 15 times 4 squared plus 20 times 4 minus 3. Now I don't have a calculator, so someone's going to have to help me out here. It's going to be a serious slope. If you don't have a calculator, come up here and grab a calculator. $317? Anybody else? Alright. So f prime of 4 equals 317. Clue, what does that mean though? What does f prime of 4 equals 317? What does this mean?
Very, very, very steep.
It is. The slope of what?
The tangent.
The slope of the tangent line. The slope of the tangent line where?
After 4.
The slope of the tangent line at 4 of what?
Thanks.
Of what?
Of this function.
Oh,
Of
okay.
this function.
So if we were to write this in a complete sentence, we would say the slope of the function, I'm not going to write the function definition down there, say of the function, at x equals 4 is 317. We found that it's helpful for students to write 1 or 2 sort of summary sentences, because otherwise you just end up with like math notation and you start turning into a math nerd who only speaks in like numbers and symbols, but never in complete sentences. I'm just kind of teasing actually, because when you get to a certain level of math, you have to write in paragraphs, proofs.
Paragraphs?
Yeah. How crazy is that, right? Okay. Now, some of y'all are a little bit more reflective, maybe a little bit more contemplative. Cody's not here. He also is sort of contrarian sometimes. You know, he's sort of like, what about this? So I can't really pick on him. So maybe Stephanie, she's kind of can be somewhat philosophical sometimes.
What?
So, Stephanie, I'm looking at this right here. F prime of x equals 15x squared plus 20x minus 3, right? This, you know, first derivative here. When you just sort of look at that, does it look like maybe any other part of the problem?
What? What do you mean?
Well, I mean, you know, I'm just sort of looking at this, and I'm looking at this as a formula, right? Okay? Does it make you think any questions? Just sort of like, I wonder if.
Mm-hmm. Makes me.
I wonder if you did like the 2 times 15 and then x.
That's what.
Yeah, right. Okay. See, yeah, we're getting there. You're wondering, could I take the derivative of this?
Mm-hmm.
And shorten the problem.
Yeah, and make it.
Would you shorten the problem? You would end up with a different expression here, and it would become smaller. Yes, your intuition is correct on that, but you would not. I don't know. Would you end up with the same number?
Hmm.
Good question. So we would need. So let's explore this. So you would need some sort of notation to indicate that you are taking the derivative of the derivative. So we will call that f double prime.
Prime.
F prime prime. All right. There is a name for this, by the way. You're not creating anything new. It has been thought of before. It's called the second derivative. But you know what? You thought of it independently with a little bit of coaching, so it's good for you. So yeah, that would be 30x plus 20. And then the minus 3 turns to 0. That's it. Okay, yeah. I can already tell you if I plug in 4 right now, we're not getting 317. If I plug in 4 right there, my mental math tells me that's 120.
Yeah.
Plus 20 is 40. Okay, so it's not really interesting. I mean, we could plug it in. F double prime evaluated 4 is 140. It's a different number. You might ask me, does that tell us anything about the graph? Like, does it tell us, since the other one's about the slope, what does this tell us? And the answer is, oh yeah, it tells you something. You're gonna have to wait till next chapter for me to tell you what that is. But yeah, it tells you something very interesting. It talks about the concavity of the function, whether it's concave up or concave down. Slope of the slope, if you will.
Oh my gosh.
But then Rosa here, just to be, herself, is gonna say, hey, Mr. Goddard.
You shorten it again?
Yeah, can you shorten it again? Can we take the derivative again? Absolutely. You could do f triple prime. And what's the derivative of 30x plus 20 going to be, class?
It's gonna be a constant for 30. So
Yeah, it's just going to be, the derivative of this linear function is a constant. So remember, quadratics reduced to linears. Linears, when you take the derivative, turn into constants. Constant functions turn into
nothing. They turn into.
At this point, we pretty much start writing. I think we do IV maybe, or maybe we just write 4. Sometimes they write F and then they put like parentheses up there. They put 4. It's weird. Okay. The derivative. What's the derivative of 30, class? 0.
And then the derivative of 0 is.
Ooh, we didn't talk about that. What's the derivative of 0?
Well, because the slope.
What would a function?
It's still 0, right? Slope would still be.
What would f of x equal 0? What would that graph look like?
It's like no, it's a
Not a
horizontal.
dot.
It's a horizontal line at 0.
Yes. Is that what you're trying to say?
Yeah.
Yes. Ivan is correct. This is a horizontal line along y equals 0. Yep, that's what it looks like. That's what f of x equals 0. Or the y value is always 0. The slope is always 0. All right, right? Because the slope here, 0 slope, 0 slope, 0 slope, 0 slope, right? So the derivative of 0, so f prime of x would be
0.
0.
Yeah.
So then from 0 you can't go nowhere.
Oh, you can go somewhere. You can go anywhere from 0. But if you're taking the derivative of 0, which I think is what you're trying to say, then the answer is
No.
Then what if you?
no. You just
I
did
mean,
it.
you do
So
go
you should just keep going 0.
It's just 0. Yeah. So f. So the fifth derivative is
0.
the sixth derivative is
0.
yeah.
Plus
My second year to teach calculus, I think, I had a student, a teacher's, not a teacher's aide, student teacher,
Mm-hmm.
match the words together. Anyway, and so we got to this point, and she created the quiz for this chapter, and as a bonus, there was this problem, and it was a monster polynomial, right? And it said find the 8th derivative.
Oh.
Mm-hmm.
And basically, after you got to like level 7 or 6, whatever, it was just 0. So it was like 0 all the way down, or anyway, or it was, maybe it was exactly 8. It was a degree 8, and it was like the 8th derivative. So you finally did all that stuff, and you got to, and it was 0. You know what I mean? Anyway, and we had one guy, and he's like, "Oh, I'm gonna get this," you know, and he's going all the way down, he's trying to figure, you know, he gets there. He's like, and then he stayed like 15 minutes after school or 30. Oh, it's something ridiculous, and finally gets down there. He's like, all that work, and it was just 0. You know. Anyway, good old Edward. So that was pretty fun. Anyway, so there you go. So we talked about the second derivative. And beyond. Okay, there are 2 very special functions that we need to do that local linearization process on. I'm going to use a little different notation here. So y equals sine x. So sine and cosine. We need to figure out what is the derivative of sine and what is the derivative of cosine. Okay? So if you remember from pre-cal, the sine function. You remember sine function starts where, class?
0.
Starts at 0 and it ends
Mm-hmm.
at 0 after it's complete one circle, and in the middle it's 0. Starts at 0, ends at 0, which happens at 2 pi, and then right in the middle there at pi it is also 0. At the first quartile, so at pi over 2, we remember that it hits its high point of 1, and then in between pi and 2 pi, 3 pi over 2, hits its low point at -1. And then bobs and weaves its way like that. So what we're going to do is we're going to do our local linear analysis on that. And directly below it, I'm going to make those marks. So looking at this class, are there any clear, what we do is we're going to, imagine, drawing little tangent lines at various locations. As if we were to zoom in and just, pick another dot right next to that one. Are there any interesting points here for the slopes?
There's 2 zeros.
Yeah, there's 0.
Okay. So when you say 0, you mean there's 2 locations where the slope is 0?
Yeah.
Where are those, Hector?
It's on top of the 2.
Top of the peak?
Yeah.
Yeah, okay. So, yeah, if we were to zoom in, we'd definitely have a slope of 0 right there. And then here in the bottom of the valley, highest high and lowest low. So if we draw one right here, we're to zoom in and draw one dot right next to the other, and then try to make that with a little line right there. We do that. If we come here, zoom in, put one dot right next to the other, we get something like that. How would y'all describe these slopes, class, in this sort of climbing up the mountain?
Positive.
Positive.
Kind of steep.
Say that again.
Kind of steep.
Kind of steep, and then kind of not so steep. And then just sort of like kind of shallow and then like really shallow, right? So, I'm gonna give you a value here just because it's helpful. I'm gonna call that a slope of 1. If that's a 1, what might this slope right here be? 0.75? What about here? 0.50? And then right here? 0.2. Sounds good. And then as we work our way here from the highest mountain to the lowest valley, what sort of numbers are we looking at here, class?
Negative.
Negative numbers. Where would you say it's the steepest?
The middle.
Exactly, yeah, right there in the middle. So I'll call that -1. We're looking at some shallow values right here. So this might be like a -0.2, and then a -0.5, and then like a -0.75. See, because it's close to 0 here, but then it gets steeper and steeper, and then it sort of reverses the process right there. Do y'all agree with that?
Mm-hmm.
So like right here, we're at like -0.75, pretty steep, but then over here, like pretty not so steep. So -0.5 and then -0.2. We'll just go with those numbers that we came up with before. And then, all right, building ourselves back up. What a great drama here, right? Okay, you've got the character rises, then he, does something awesome, reaches his peak, but then he, gets defeated and faces some troubles and goes down, loses, someone very close to him, but then he's going to rebuild, right? Rise from the ashes, okay?
Lose again.
And there we go, rising back up here. I probably should put another one there. So we've got slope of 1, and then we can see here 0, and then it's beginning to get kind of steep, so it's around 0.2. We'll do our 0.5 and then 0.75. Okay, we definitely see a pattern there. The question is, what does that look like if we start graphing these slope values as y values down here, right? So let's do it. So at pi/2, I'm going to graph an up-down value of 0, sort of my anchor points, and then right here at 3pi/2, my up-down value also of 0. I'm going to start off at 1, and then sort of work my way down to 0. Right here, I'm hitting my lowest low of -1, so I'm going to put that down there. And so notice I leave that 0, and I go -0.2, -0.5, -0.75. So kind of something like this. Hit that -1. Then I work my way back up, and then I 0.2, 0.5, 0.75. I'm working my way back up to that 1 value. Oh my gosh! What does that look like, Rosa? It looks like cosine. All right, and another notation here, since I need to expose you to, instead of saying f and f prime, I do want you to remember that you can say y and then dy over dx, okay? So that's going to be cosine x. That's the cosine graph. Oh my gosh. The derivative of sine is cosine. Whoa. Makes me wonder what the derivative of cosine is.
I know. That's true. Could it be?
Is it like the tangent?
Yeah, I don't know. Let's tell you what, we'll find out tomorrow. I'm going to give you this homework right here. We'll do a couple. We'll figure out what cosine is. We'll solve a couple of these. This homework is still going to be due on Wednesday, but it won't take you that long. We will do a few of those problems together. Today we talked about the derivative of sine, second derivative and beyond, derivative of a constant function, and then kind of review that other stuff. Lots of good stuff. Yes. Okay.